So it's getting recorded, right?
Yes.
Yeah. Your first question is for perfect square. So given a positive integer n, find the least number of perfect square numbers. For example, 1, 4, 9, and 16, which sums to n. So for 12, all 4, 4, 4. That makes it to 12 and each of them is a perfect square. For 13, 4 plus 9 is a combination. Yeah. So how to proceed here?
Okay, so we don't have any
Restrictions, right?
restrictions here, right? Or do we?
No.
Okay.
There
So it's just a positive integer always, and then we have to find a perfect square, the sum of perfect square, right? To that integer. Okay. Yeah. So this looks okay as per. There are no constraints, nothing to be clarified here on the requirements front, right? Yeah. Yeah. So how do we think about it?
equation only, right? Or like keep on, what do you say? I mean, you get the first number 1, then the remaining will be 11, and again go for 4, then remaining will be 8, and all the 3 paths I'll check, right?
Okay. So you are saying like you'd start with all the numbers, all the square numbers.
Yeah, all the,
Yeah.
like, if I take 1, then remainder will be 11. If I take 4, then it will be 8. If it is 9, then it will be 3, and so on. We'll keep on doing,
Okay.
right?
Yeah, you
I mean,
further recurse it. Okay.
yeah, and whichever path would be shortest, that I should
That will be your value. Okay.
value.
So this is good. So you are saying it should be done recursively.
Recursively, yeah.
Okay. And then for that you would need some inputs, and that would be like either you pre-compute all your squares before even passing it to them, right? Or you can do it on the fly. That is
On
also
the fly
possible.
also. Yeah.
Okay, yeah.
Looking this, it looks like we can even use this BFS there.
Oh yeah, BFS.
Yeah, that also looks good. So can you explain more like them? I mean, on this only you will traverse BFS to find shortest path, right?
Yeah, so it would be like let's say initially if I start with 0 and what is the example here?
12.
It's 12. So what I can do is like there could be 1, there could be 4, there could be 9. These all are under 12. I can't take 14, 4 because it will be 16. Then now the next thing could be again starting from 1 and adding to this guy. So it will become 2. Then we'll have 5, and then we'll have 10. Over here, we can still start from 1, but we already have seen 5. So that will be a repetition, like how we do. I can have a visited also. So where I already put 1, 4, 9, 2, 5, 10. So don't need to put, so I can have right now 8. And if I take 9 and 4, it will exceed 12. So there's no advantage of taking that. And then here it could be 10. Yeah, if I take 4 here, it will become 13. So I don't want that because it will exceed my limit. And then again coming here, 3. 3 could be possibility. 6 could be possibility. 11 could be possibility. I'm just doing from again taking 1, 2, 4. Sorry, 1, 2, 3, 4. And again it could be 6. 6 we already have seen, so not interested. And then 4 plus 9. 9 we have already seen, not interested. And yeah, so here we can't go further. Here we can go 11. 11 we already seen. So here also we can't go further. Here I could have 9. 9 we already seen. Then if I add 4, it will become 12. So as soon as I reach here, this is using this three uh, 3 levels, I could reach 12. There could be other possibilities, but this is
Yeah.
one
Yeah,
background.
but I think one question, why are you using 2, 5? Instead of that, if you would have used again the square values, that would have been better,
No,
right?
I also need to see if I reach my sum or not.
But the sum should be with the squares of the numbers. So
Yeah, so that's what this is a square of numbers. So if you see this 5, how it came, it is 1 square plus 2 square.
oh, okay, okay, okay. I got your point. So you're adding them.
Yeah.
Okay. Okay, makes sense. Yeah.
And then with BFS, when we reach this level 3, we got our guide.
Yeah, yeah. So that is the shortest path in that case.
Mhm.
Yeah. So you start with your root as you push the first one as 0 in your queue, and then you start from there.
Yeah, so here it was like 1 square, this guy was 2 square, this
Right,
guy
right.
was 3 square, and then followed by this was 1 square plus 1 square. Yeah. And
Plus
this
1
we
square
already.
plus 2 square. Yeah, yeah. That makes sense. Yeah.
You also can start the root, as the target, right, at the sum.
Yeah,
I
it
think.
could be either way. We can start with 12 and go make it reaching till 0.
Yeah.
So in that case, the number of steps would be the same.
Yeah. Do you think it will be different?
No, I don't know it.
No, actually it should be the same because that is what the level is, right? So the
Yeah,
shortest path.
either
Yeah.
you go from like this, it should be same. Now you're
Yeah.
subtracting. It will become, I think, 11. It should become 8. It should become
3.
3. So again, this was 12 minus 1 square. This was 12 minus 2 square. And then here. Again, it will become 4, and then here somewhere it should become 0. So
Because I see the other way. When we root at 0, there's a lot of duplicate there, right?
no,
I know that you have a set or some sort of to remove the duplicate, but we
you will get
still
duplicates here also, I think so. Duplicates will come this side also. I don't I I don't see it should be a reflection of this. I don't see it should be other way around.
Yeah. I agree.
Here you are doing so I don't see any computation values will get changed. For example, when we were having where we saw duplicate, we saw somewhere here 5. Somewhere here we should end up like 5 when we are subtracting
Yeah, so whenever you see a duplicate, you just ignore it, right? Because you're
Yeah,
storing
we
that
have
widget. Yeah,
this is like a standard BFS.
BFS. Yeah, yeah.
You see a visited, we just ignore because we have already seen it, so we are not interested in
Yeah.
process. Or thinking that we have seen at the lower level, so why we again put like at a higher level.
Correct. And I think using a BFS level or traversal is much easier than doing other approaches, right? Yeah, it's more
It's a
efficient.
standard DP also, right? Repeating sub problems are there. It's one and I mean, both will be same only, right?
Yeah, you can have a DP solution for sure,
Yeah.
but this approach is a BFS approach. So I was just comparing, the way DP is slightly, on the other side. Okay, we can be doing it, but it's slightly complex. Sometimes it's tricky to implement. Yeah.
Yeah.
So,
How's the DP solution work? Is that similar like this?
Yeah, tree will be same. Just check the repeating sub problems and whatever Asim was explaining, same thing. Like, I mean, each time you take the square of
Then it
the.
would be the optimal, right? Because they do the breadth first search too, but they also have DP.
Yeah, that would be a bit more optimal DP, I think. No, but here also you can memorize BFS, like if he sees the notes, but that will be taken care by visited, right? If the notes is already seen, so I think in that case,
So by the time
visited.
you see a visitor, you only know that you're not visited, but for DP, would you already save the result in the DP? You say, okay, I visit this, and then the result to reach this node is X, so I can get
Use
from
it.
that.
Oh,
Yeah.
yeah. But I don't think so much difference will be there. So you're telling you will be able to reuse the result in case of DP, right?
I don't know why. Based on what you said, I don't know how DP work. You say it's similar to that, right? Do the breadth first search too?
Yeah, I'm storing like whenever I find same number repeated, so I'll store the result for that. And in the subsequent bigger step, if I find that this is repeating, I'll pick the value from there. A tree will be same, what for DFS and DP.
so are you using a bottom-up approach, Shashank?
No, top down itself.
And then you're doing a memorization?
Yeah, just memoization I'm using. Like I can I'm declaring 1D array, and similarly I'm going from 1 to n plus 1, and for I'm checking the numbers from 1 to what you say till the square root of the number, like 12 square root. I mean calculating the square root of every what you say I, and subtracting it from n, so I'll get branches, right? This is the recursive equation, like 1 plus
But this is
I'm
bottom up.
the bottom of, but yeah, I mean not typical bottom up like 2D matrix you'll have here, you can say, but yeah.
But because you're starting from like one only, then you are moving
Yeah,
towards.
the n plus 1, I mean n plus 1, because it last value will be deprecated, that's why.
Yeah, you are just traversing one, like once only, you're not going back and forth.
Yeah,
As in case problem.
yeah, bottom up it's only, you can say, but top down also it will be same only, right? There also you will store the results and
Top
just make
down
use.
to recursive.
Yeah, top-down will be recursive. And then in that case, you will be slightly doing the way the BFS what Asim was showing. You will actually have some for loop starting from that to the current one. And then you will be subtracting when you're actually putting it for the next
Yes.
recursive relationship. You'll be just subtracting the value. Or the other way you showed like adding the value, right? So
Yeah,
yeah, but that will be sort of a DFS approach than what he was showing. Yeah.
yeah, I have heard that also, what you are saying.
Okay.
This is what you are talking, right, for BFS approach. So I'm creating first the square of all the numbers from I to till the what do you say number, till the root of that number,
Mhm.
and Just I'm pushing initial. This is my queue in which I'm pushing my number first n, and this is a visited set n queue. So as long as my queue is not over, I'll go for through each of the queue, and then for the squares that are present here, if I find that your node is equal to square, you will return, and if node is less than square, then in that case you'll break and just again whatever square you got, that you subtract from the root node to go for the next level.
Oh, so this is a BFS approach, right?
Yeah, BFS approach.
Yeah,
I think Ronnie wants to speak something, but
yeah, he's having a bad audio. Okay, so this is the way.
he's
Okay.
saying something.
So this is what Asim was also explaining, correct?
Yeah. Yeah, if Asim wants to share.
I can share. So okay. So this is, I think, the standard BFS uh, level audit reversal. You go by levels, and I think Shashank has computed all of them beforehand, so
Yeah.
that would be optimized. So I'm computing every time, adding to this, putting here, and creating.
Yeah, this is a standard way of doing it. Yeah.
BFS.
And looks like we can clear the visited here. We don't clear also, that is also fine. But we don't see a difference in different levels.
No, if numbers are repeated, then
Yeah, but they won't repeat on different levels.
yeah, that's why we are resetting.
Mhm. I think if I don't do out also, that should also work. I think I was just playing around.
Let's try.
Should work because it was just optimized just to make it.
Oh.
It should work. Okay, I think that's
Can
it.
you submit it, Asim? Because it may work for this small test case, but it may not work for the
No, it will work.
other test case.
It will work because it's just clearing the hash set. If it is working with clearing, without clearing, definitely it will work. Try that.
Then why you put the visit there in the first place?
Which one?
On line 27.
No, this is just clearing the visited. So basically, what I'm trying to say is, that we don't see repetition at different levels because we are adding things. So if it is 149, then here we get 5, here we get 5, but 5 cannot come at any other level.
Yeah.
So I think, playing around with that. That's it.
Yeah. But it's very hard to come like that, but the standard way would be without doing that. Yeah.
Yeah, standard way, don't, yeah, I would recommend don't go with the standard way. It's just optim because it's just trying to see whether this theory is correct or not.
Correct. So, but it's good to know. Yeah. Yeah, actually, Ronnie had some question in the chat. because he has very bad audio for Asim. He's saying that about the level, the repetition, what you showed just now.
Whether there will be repetition at different levels or not.
Right. Yeah. This is okay. Yeah. I think he demonstrated also, right? Yeah. Yeah.
So
So we have a DP approach, now BFS, right? And then
one is Legender's theorem. Like every natural number will always be a square of 4 numbers. I mean, what I said, like, and there is a number n. You can write it as a square plus b square plus c square plus d square in that format. And
Yeah,
what,
I think that is also one thing. Yeah, using like theorem.
but that we won't be able to recall during interview, right? These are like a bit more.
But it looks like we can say that it cannot go beyond 4 levels. Just it.
Oh yeah, from that.
Think like a test case, unit test. Like if it is coming giving you 5, that means something is wrong with the solution.
Exactly.
oh.
Yeah, that's a nice mental. But who knows that theorem? Then only we can. What do you say?
Yeah, if you recall, I think that's fine. If you couldn't, then nothing can do.
Yeah.
If now you told me, I could have recalled it. If I remember it in a real interview, I'll just at then throw as a tantrum that hey, there could be. Looks like there's some theorem, and it says we can't go beyond 4, and I can add a test case around that.
No.
Yeah. So the BFS or maybe the DP should be sufficient, right? Yeah.
Yeah.
So, but what was the theorem actually? It is like you have 4 numbers, square numbers, right? And if you have some, that is the maximum numbers you can have, right?
For any number, yeah.
Yeah. So if you first you try with 1, because if your some number is that perfect square, that will be 1. Or else you do it for 2, then you do it for 3, and at the end you just return 4, something like that, right?
Exactly. Some more, I think, I don't know. I'm not able to recall, but something a little bit more information was there.
Yeah, but okay. So coming
Crux
to
is like every number you can represent as a 4 perfect square, sum of 4 perfect square, unlike the way you explained.
yeah.
So I think, do you have?
No, it's not perfect square. It's just integer squares.
Sorry, I mean the other way around. Yeah, square of the numbers. Yeah,
I can share this if you want, like this solution.
you have.
Yeah.
You can share it.
Yeah, this thing. As you
Oh,
said. Yeah, it sets the upper bound for the result.
so yeah, here 31 is expressed as 5 square 2 square plus.
Yeah. Then there's another theorem.
It will be a multiple of this, right? 4 raised to the power k into. Then we express the sum of 3 numbers.
Yeah, it's purely mathematical.
Yeah, exactly.
Yeah, because like you can get like if it is a number 1, that's very easy to find. But to find number 2 and 3, is actually you'll have to take support of these theorems, right? Because if you go for 2, you'll have to do something recursively, which will actually consume more time that you're gonna do. So you'll have to first eliminate if it's not 1, and then if it is not something 3, and then come to or return 4 or return 3 something, right? What they have done here, yeah.
Yes.
So he says like on line 10, he just divides that by 4 because if it's divisible by 4, and then actually he just looks for its modulo of 8. If it's 7, then return 4.
So
You
that
know, if
8m plus 7 is following, right? The remainder will be 7.
right.
Yeah.
So
Okay,
if
so
you have 7,
why is he doing this?
You go to the
because
top, drag a little bit. That theorem was written of 4 raised to the power k into 8m plus 7.
okay, but
Yeah.
7, if you break down, if you see, that will be like 1 plus so
Y plus 1 plus 1. 3, 1 plus 4.
3, 1 plus 4, right?
4. Yeah.
Yeah.
3, 1, yeah.
1 square.
Yeah, 1 square. No, but if it is 7, you are just dividing by 4, so that you won't count. You will, right?
We'll have to
That will
count
be
now.
1.
Yeah. There has to be some proof for this, right? Or from observation, it might be.
Yeah, it's a long description. Like,
There are a lot of things they mentioned.
Can you also discuss the time complexity with the previously discussed solution?
sorry, Uday, come again, please.
I mean, the DP one and the BFS one, what will be the time complexity for this?
Order of number of levels, like log n.
Why
Mm,
log?
But before that, we'll compute squares.
I think it would be the way Asim explained. I think it would be n into the root of n, because for every number he was going till the root of that number, I think, right?
Element. Okay.
No, I mean, the DP approach seems to be somewhat slow, but I think the DP approach is also n root n itself.
Yeah, in the most optimal case, it's n root n. I'll show you that also.
N root n.
Yeah.
Yeah, because like, okay, we'll go to that first. I think this is the one.
Yeah. Yes.
Yeah, here. So this part, this would be root n, right? So he's running his loop till this only, because we do not need to go any further after root n.
Yes.
So for every n, it will run till root n, right?
Yeah,
And not for every 1 to n. Yeah.
for every I, right?
I too. Yeah.
Again, he's
Yeah,
pre-computing also for this only, like max square index.
yeah, this will be n root n, but this seems to be somewhat slow than the BFS approach.
Okay, is it?
But here we are doing much more optimization in DP, right? We are reusing the things which we have already seen. So technically, this should be much more better compared to that of BFS. But
Yeah, this is better.
They have given very complex time complexity here.
yeah, polynomial kind of, not polynomial. H by 2 it is, right?
So in the worst case, what can be the height?
Log n. No, n. I mean, you skewed tree you will get one
No,
single.
height will always be maximum 4, right? It has to be 4. It cannot be
Okay.
more than 4.
Yeah.
Right. this is n square, right?
Yeah, n square. No, but if it is, let's say, okay, n square, yes.
The worst case.
Then they could have directly hard coded the value O of n square because height will always be fixed 4, right?
They might not be using that part, that theorem for this explanation.
No, it is, like anytime your answer cannot be more than 4, correct?
Right,
Yeah.
right.
So the theorem is different, yeah, but in this case also. So if it is 4, then you will go to maximum 4 levels always.
So in worst case, it will be n square, yeah.
How can that be n square? N is something different, right? N is the
4
input.
by 2, right? He's saying h
No, no,
is
4
4.
by 2. Yeah. 4 by 2.
4 by 2.
N raised to the power 4 by 2. Like h is 4, right?
Okay.
Yeah.
That is the way you are saying n square.
Yeah, yeah, yeah.
I don't know. Maybe. Okay.
But by this one, if we see that DP should be faster, right?
Yeah, looks like that, but
Right.
Yeah, but I tried submitting both the ones, but even the discussion, but the BFF seems to be somewhat faster.
Better, yeah. It looks like, yeah. Because if you are storing all the visits at once, the way he's doing at each and every level, you will be optimizing that, right? So you're using each and every that factor only once. So therefore you are actually, it will be root of n, whatever that value will be, into
But
number of levels, 4 into root of n, I would say.
but the branching factor is still root of n, right?
Yeah, this looks to be a GP, sum of a GP, right?
Yeah, the branching
Common
factor is
factor.
root n. Might be.
yeah, at max root n branches would have, right? For had it been 16, then 4 branches would have been there, right? 1, 4, 9, and 16. Yeah. Yeah, it's a bit clumsy, like.
Yeah, it's slightly difficult to understand, but maybe it's like O of root n. I don't know if we say h equals 4 in that case and substitute, that might make sense. I'm not sure about that. But if you just ignore h for now and keep it some value, so it will be root of n, right? Of
Let's go to the
root n.
maximum number of recursion that will happen.
Entire tree to find the solution. That means entire tree means we have to travel the entire tree to find the solution. Yeah, let's see the code at least. Like, I mean,
Okay. So we have only 4 approaches, right? One is the DP, the top down, the bottoms up, the BFS, and then the mathematical, correct?
yeah, legendary term, yeah.
Okay.
But
So
what hit here for the first time was DP only. I mean, BFS looked like out of box little bit because we have choices right here. We will do all the possible branches and take the minimum path. So that was straightforward, isn't it? Or
which one you are talking about?
I'm saying that DP was much more intuitive in this problem compared to BFS. Like BFS was bit out of box, you can say, like not out of box also, but
Yeah, it doesn't come directly saying, okay,
directly,
this problem is. So usually you try to,
Okay,
mostly I would go for this one, right? The recursive way.
yeah,
but
yeah.
they have mentioned the least. So as soon as you see least, then it could be intuition.
But by that logic, we can have that also. Like, least they are telling and options we have. So DP can also hit. Yeah, I mean,
Okay.
DFS would also hit.
Least of purpose square, that might give a hint. Okay. But this is
Yeah.
good to remember, right?
Exactly.
Yeah. Least number is like a shortest path. Yeah. But coming up will be slightly difficult. Yeah. But yeah, if you just think of it, maybe possible. Yeah. That's right.
Yeah.
Look.
Yeah. So we can go to next then. So our next is like number of matching subsequences. So a string is given and dictionary words of words. We are supposed to find the number of words that is a subsequence of S. So a string is given and these are the subsequences of that string. Sorry, we have to find which subsequence of it matches in this. So BB is not possible. A is possible and ACD is there and AC is also there. You know. And constraints are like all words in the words and S will consist of lowercase. And length of S will be in range of 1 to 50k and words will be 50,000. Sorry, 5,000, right? 5k, sorry. And length of words I will be in the range of 1 to 50. Yeah. So the brute force here should be like generate all the possible subsequences out of it, right? And see if that matches with your list or not.
No, actually, I would say like instead of going that way,
Yeah.
take each and every word, okay,
Okay.
and see if it is a subsequence in that S, right? So just use something like a 2-pointer every time, and then keep on incrementing the pointer of the second one, okay, where it matches with its character matches with that S. At the end, you see if you have reached the end of that particular word, then you can add that to the answer.
But yeah, I think a 2-pointer should be good, and I think that is a technique which we can use a lot of places where we have to compare two strings and see it's a subsequence.
Yeah. So how will you skip the characters like, oh, I mean, initially both the pointers will be at A, right? You found A, now you will increase the right pointer, right?
Yeah, what I was thinking, like you start a for loop for your S, right?
Okay.
And then you have a just pointer for your word. Like, for example, if your word is A, C, D, right?
Okay.
So then you have a pointer inside that for loop for your ACD. So the ACD pointer will be pointing to A. As soon as your outer A matches with A, so your for loop will always increment, right? So in that case, you just increment this inner pointer of the ACD. Yeah, you move to C, and then you keep on moving to this till you reach the end. And when you reach the end and you're out of the for loop, you can count that if it is reaching to the end of that.
So basically, if you reach end and that is the length of the string, we are good.
Right. Yeah. Actually, this is an efficient way of doing it, but in this scenario or in this problem, actually it doesn't. It hits on a TLE. So
No, for me, it didn't hit for TLA.
okay. Yeah.
But yeah,
So
the runtime was still on the higher side.
right. So they are saying, like you have. I found a test case wherein your A is very big, S is very big, and then most of your words are repeated. So maybe the requirement clarification should be here, because in the example he's showing all the words are unique, but what if we have all words same? Most of them are repeated.
Yeah, so one thing is like we can even have a sect. If you have already computed, let's say we have ACD again, then we can put ACD in the sect. Like, okay, I have already seen and did that. So if next time ACD comes, don't do it.
Right. So instead of set, You know, because what will happen if your ACD matches, but if you have something like AZD every time,
A.
AZD, you know, something like that, which won't match actually.
Oh, then we need both of them.
Yeah, so maybe instead of set can have something like a map, true or false, something like that, and then use it.
Oh, so basically both of them seem.
Sorry, I didn't get the set part. Like, why are we putting them in the set?
Well, actually,
Right.
there is a test case, you know, if your S is very big and your input words, okay, they are all repeated. You have many of them repeated,
Okay.
right? You can have ACD, 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 many of them. Like you say 5,000 or maybe 1,000. So you will be repeatedly doing the same thing over and over again, correct?
Right.
So for that, what you can do, Asim suggested, like you put that in a set, you know, once you have seen that, okay, you put that in a set. So next time you don't have to compute it for the next word. You just copy that. Yeah.
So it's better to put both of them.
Yeah.
If you computed it, whatever the result was, put both of them in the set. So basically, think in that way. ACD is a kind of a true positive, and then you have AZD, and then you again have AZD a lot of times. So we end up computing all of them. So there should be a way like this is true, this is false, and if I got them again, then I should be knowing. I should not again go and compute AZD.
Yeah, you can use the count.
Count or anything like that. Here we don't need count. We can even work around with. I think.
Yeah. So whenever it is true, you just increment the answer, right?
Yeah, either way. Yeah, true. Keep true or false. That is should be fine.
So maybe have two sets, one for true, one for false, and then you put in
Or
those two sets.
in
Yeah.
the map itself, we can keep true false.
Yeah, in the map you can keep. Yeah, that is true. Yeah, so if you use that optimization, then it works. At least it gets accepted, and also I think the time complexity is good, right? Yeah. Yeah, but they say you can further optimize it, and then so you can do more differently. Yeah.
I tried little different. I mean, like almost same. I think so, but I pushed all the words into a queue, and for every character in S, checking whether all the elements in the queue have that starting word. I will remove the first character and again push it back. And when I got an empty string, that the point where I count, I increment my count, and I do that until I finish all the characters in S.
So when you said like you put in a queue, and if you have at the top of the queue some node, some word, then you actually increment its count, its index, right? And then you put back again in the queue.
I'll generally pop it. I'll remove that from the queue and check if it has. If the first character is same as the character which I'm looking now in the S. If it is same, then I'll remove the first character and again append it back into the queue.
Can you draw that like it will move?
So, but what is the intuition to do that?
I was thinking like like okay. So okay, let me.
So one thing you usually do, you know, because your S might be a very big one, right? You don't want to do traverse S over and over again, correct?
Yeah. So that's why like, here they gave the size of S could be like 5 into 10 to the power 4.
50,000 something, yeah.
Yeah. So and also the size of words could be 50. So I thought maybe you pushing all those words into queue, like everything into the queue. Uh, uh, then first I'm at character 1 is so I will see if this has a character A. Then I'll remove this and put at the end empty string because it has only one character. Then I go here, it has nothing to do. Then I'll put the same string again back. For this one, I have A, so I will slice it. I will remove this, and at the end I will put as CE only because I removed the A in this. I don't like this way until I do until I reach E. Which are all the strings that was empty, that many subsequence words are the subsequence. So every time I get a empty string in the queue outside, I'll take it as a count.
Okay.
Yeah, but
That
this giving TLE, for me it's giving TLE, but
oh, it's giving TLE.
yeah.
Yeah, because you are actually putting in the queue over and over again, right? So that is also, you might be you might end up doing more strings frequently.
I was thinking like as S is very large and size of words is very small, so I thought we are going only once over the S and number of words. So I'm checking for each character with all that. But
Yeah, that is good. But I think what they have suggested, that is a good approach what you're doing. You could have actually bucketed all of these words in with the starting letter,
yeah,
like if
yeah,
your starting letter is the A, then you can form a string of words like A, AC, ACD, ACE, and then actually you run through your S, okay, and then you look for the first word what is in that S, and you try to go to that bucket. You clear all those first letters of that particular words, and then you put back into the queue with the same, using the same logic of looking for the first
first character.
character. Yeah.
Yeah, I got it. So I can ignore these kind of BB in terms of A starting with A. Like, yeah.
Right. So that is optimum or maybe optimized way. That is what they say. But I
But
think
if all
what Asim was suggesting also is giving good time complexity. Yeah, go ahead,
but
Shashank.
I was saying if all the words are starting with A in your word list array, then again everything you will put into your queue, right?
No, yeah, you can use a queue or whatever it is, but what they have suggested, use something like an array and then array or something like that, because you have all of these are lower case characters, so you can have an array of 26, and then you can have each an array will have a list of all those words, right? Something
Yeah,
like
but
that.
that array size can be very big also, right? If all the words in this, all the subsequences start with A in my word
Yeah,
list.
it can be, that is true. But what you are doing is you are actually focusing on only on those words which are starting with that character for which your S is, because traversing through S will be more expensive as it is a very big number, string, right? In case where the string S is very big. So for that, if you want to optimize, so they say this is a better way of doing it.
So yeah, first you finish with A, then with B and C. So like first all the letters starting with A you will cover up.
Right. So whatever is currently your S is at, you just go and traverse for each and every letter in that, because you have to only focus on a particular bucket, right? Now in this
Yeah.
case, first is A, so you look only for that A bucket, you get all the list of all those words, and then you remove your first words, and in case if you reach the end of the string, you can increment the answer, just ignore it, don't put that back in another queue or another bucket, right?
Yeah. Yeah.
So that can be done, but actually that is very, what you say, focused to particular test case, right? Because if you are given such a test case in your interview, or you come up with a test case, then actually you can think about that solution. Or
Yeah.
else the way what Asim was discussing will be the very generic way to do
To
that.
do
Not only generic, very very efficient way also of doing it, right? Because this is one of a corner case to handle, right? If you
yeah.
think your S is very big and you have many repeated words.
So yeah, yeah. But your constraint is like we are avoiding the repeating words. But In generic, it can.
You can use, I mean, if even if the string is bigger, you can use binary search kind of thing.
Okay. So how does the binary search might help that?
Actually, this is actually, I thought this will a follow-up question of. So there is one more question. You just need. So the question is, if you are given two strings, you need to find whether one is a subsequence of the other or not. And the follow-up question was, how do you do it for repetitive queries?
Oh,
So
okay. Uh-huh.
yeah. So in one of the solutions, they described that you can actually maintain. I mean, you can actually pass that as string s, and you can actually keep it as what are the indexes for A and what are the indexes for B, C, D, E, like that, and you go through the words. So you first try to find the first index for A, and you take that first index and try to find what will be the next index for I mean, let's take ACE. You take the first index of A, and next you take this index and you try to find uh, what can be the next index after A.
But when you are saying index, you mean to say you want to store the index information of the string s somewhere?
Yeah, so A, every character to a list of indexes.
Okay, but then in that case, if you have duplicates, then how are you going to store that?
That's fine, right? I mean, so A can be repetitive. So I will take the first index, and suppose there can be ACA as well. So you will take the first A and try to find what is the next C after this A index. For that, I will use the binary search, and I will take the first C and I will try to find what is the next next A after this C index.
Mm-hmm. But I'm not getting the binary search part. Can we take
So
an example?
so A indexes can be multiple, right? Let me share
Okay.
the screen. I mean, maybe the solution can explain.
Okay. Okay.
So I will try to go to iterate over the string s characters,
Okay.
and I will try to maintain the indexes for character A, character B, character C, character D, all of the characters,
Okay. Uh-huh.
and then I will iterate over the words. So I will check what is the first index for letter A in this map to list of indexes.
Okay.
Then I will use that as the first index, and if the next letter is B, I will try to find the B index after the index that I got from A.
Mm-hmm.
So if it doesn't exist, I will return there itself. If it exists, I will use that as the current index, and I will try to find the next character after this index.
That's correct. Yeah. Okay.
Yeah, till you will do this till the last character.
Mm-hmm. But then, where you will be using binary search to
So,
find the index?
so for I mean, for finding the next character, you need to use binary search.
Okay.
So you need to find the next B that is after this A's index.
Mm-hmm.
So you're
So,
running binary search on the indexes itself, right? Because they are only
Yeah,
sorted.
yeah,
that data structure you're telling is like a map with each character with all the indexes of that character
sorted.
in a string sorted.
Yeah, yeah.
Okay, okay. So on that you are doing a binary search to find seal or something
So if,
of
Yeah,
if
the.
create. Yeah, seal you can say.
okay,
Yeah.
so if you have a map for A, you have like 1, 3, 7, something like that, and then
Yeah,
for C, you are having 5, 6, and 10.
yeah,
Okay, and then for D you are having some, okay, you again have 4 and then something like 11 and 12. Okay, so in that case, when you are looking for A, C, D in this case, okay, so for
Yeah.
first A you come here, right? So
Yeah.
you can take
So
the
I will
first.
take
Uh-huh.
I will take 1, and I will take 5.
Okay, then you will take
And
5.
yeah, I will
Uh-huh.
use this 5 and binary search in the D's list. So after 5 there is only 11. So
Okay.
1 for 11 forms that.
Okay,
So for D you have to use a binary search to find the better one after
Yeah,
5.
even C, for every character we
Yeah,
need to do a.
yeah, got the point. Yeah, okay.
Yeah, so
So
are you
there
going to
it,
do for the first character also? Like when you try to find A,
That you might not need it. You can take the first itself.
the first, I mean the first, what do you say, that first non-taken character, right? No,
Yeah, yeah.
anything would, we can take
Yeah,
anything.
the first index of the first character of that string.
Right.
okay.
I think Ronnie shared the code for the same approach in the chat.
Oh, that's good. Okay. Okay, so this is good. So do you have something to share? You want to share that? Yeah, Uday.
Yeah, 1 minute, please.
Okay. Ronnie is also something.
So I'm going out through that S string of S, and I'm creating that character to tree set of indexes in this loop, that's 7 to 15, and then I'm going to the every word of that list. So I'm trying to find so if there is a set for that particular index or not. If it is there, if it is not there, I will break here itself and go to the next string. If it is there, I will try to find what is the next index for this previous index. So when I find the next index, I will set this to previous index. And if I is that last character, I will increase the count.
Okay. So your indexes dot higher is what the binary search is, right?
Yeah.
Okay.
It's the upper bound, right?
Yeah, our upper bound, yeah.
Yeah.
Yeah, this is a good one.
Okay, yeah. Okay, so actually I think Ronnie is not audible, but whatever he has shared, I'll just quickly go through that also. Just give me a minute, yeah. So this is what Ronnie was sharing. You guys can share, see this, right?
Yeah.
Okay. So he's doing the same thing. This is a function, but he's using an unordered map. And then he's actually mapping with each and every character the index. I think exactly what Uday was also doing. And then he's iterating through each and every word and just looking for this is present. And if it is present, then he's actually incrementing the count. So in is present, actually he's going through the word, this word in this for loop, each and every character of the word. And then here he's doing that upper bound, the binary search. Okay, so he's using the help of this map, right? So this is the map start and end, and then he's looking for the index. And if they match, and then if they don't match, then he returns false, or else he keeps on assigning this index to the upper one, whatever you are actually getting from the binary search, and then returns true. Yeah. So they are the same, but this is a C++ version. Yeah.
Santosh, and line 12, you say that m.ch.n, that means the last index, right?
Which one? Line
Line
number.
12.
Oh yeah, here actually he says that when you go to upper, when you look for end, it is the end of the you are not able to find out. That is what it means. Therefore,
Okay.
it reaches the end of that map.
End doesn't mean that the last element in the
No,
vector.
it means after last.
Okay, okay, got it.
So you have like in a string, you have that last terminating character, right? So that is what it
Yeah.
means. Yeah.
Okay, okay.
Okay. Yeah. Thanks,
San,
Ronnie. Yeah.
so Santosh, when you're saying like maintaining the true and false for each word,
Uh-huh.
can you quickly just tell about it? So if there are repeating words, then what are you doing?
Okay.
Saving it against true.
Yeah. I'll just share that.
Hmm.
Okay. Just a minute. Yeah. So this is the way I was doing. I'm actually maintaining a map with string and a boolean variable. So then I'm going through each and every word. This is the word. And then this is my map. Actually, I try to find if that string is already exists in that map. If it doesn't, then actually go through this our two pointer approach. Okay, so the I pointer actually traverses the S and the J pointer traverses the current string, which is the word. Okay, so whenever I find these two, actually increment that. So when I come here, that is where I actually look for if it is the end of my current word, then I store in the map as a true. Okay, but if I come to an end, if I don't find that word, okay, so still I have to store it, right? So I'll store it as false. And then when I'm done with this, but when I encounter that string again, okay, then I look for if the strings was true or false. If it was true, then only I increment my answer, right? So what I'm trying to do is I'm trying to maintain a map, and every time when I encounter a string, I look for whether it is successfully completed its sequence, like here in this case, right? So if it is completed, then I mark that string as true, or else
Mhm.
if it's not, then I mark that as false. So whenever I encounter the same string again, I don't go through this two pointer approach. I just go and look in the map. Whether it is true, then only I increment one answer. And for the false, I just ignore it.
But then if else should have been before, right?
Sorry, come again.
So the if else part which you wrote j equals m, that part. So you're already iterating the string again in the while before if else, right? I mean, I thought the if else part, like the storing in the store, should be done before iterating through the next string.
No.
Not
So
this.
here I come in this if I come only when I have not visited the string at all. So for the first time when I visit a particular word, right? If I have
Yeah.
not actually visited it earlier, then only I do this.
Okay.
Yeah, because the store count means it looks in the map and tries to find if I have that map, this string already stored in the map. If it is not, then I actually go in this if part.
Okay.
Yeah.
Okay. Yeah.
If you sort the words, would it increase the overall runtime complexity?
I don't know. Yeah, that's a good question. It might be. But even if you look, this one was not a bad time complexity, 94.91%. Yeah, the timing is something like 336 milliseconds, but not that bad. So
This is m into n, right? The length of s word into the number of words in the array, right?
yeah,
Complexity.
yeah, because you are actually traversing it always, but only thing you are actually storing those strings always. Yeah, you can say that. That's true.
Yeah, and what about Uday's and Ronnie's code? What it look like?
Ronnie's code. Yeah.
Yeah, the complexity.
I think Uday should be in a better position to address that, right?
Yeah.
because it becomes trickier when you actually use binary search, right?
Yeah, so this binary search would be a log of the length of S word, right? In worst case.
Yeah,
And we
n
have,
into log m, n
sorry,
into log m kind of thing. Yeah,
yeah, yeah.
So
Number of
it
words
will
in the
be
array into log of the length of the S word, I think.
okay, log of s, right? So whatever the word size is, okay, multiply by the highest character, and then log of s, correct?
yeah.
Yeah.
I mean, it is not tighter bound, but you can say that.
Hmm. Yeah, but it's very tricky to come that way.
Yeah.
Yeah. Okay, no problem. Good. So we might have an interview question follow up on that itself, and that will be a bigger one.
So you actually used a map, right? I mean, the try kind of thing. So, I mean, uh, there is a similar question actually. So you need, instead of finding subsequences, you need to find whether those words occur in a string or not.
Mm-hmm.
So they kind of build a tree, and I mean, there is one algorithm called la hope or sake or something. So they build and try out of that words itself to decrease the duplicates, and they, I mean, they change the try as well. But I mean, it is similar to your approach that you're saying.
Okay. Uh-huh. So you make a try, so you will actually reduce the number of words also, right?
Yeah, number of words, but they use the try to actually form some state machine as well.
Oh.
Somewhat complex, but
Mhm.
uh, yeah. So they do in that linear actually, n plus m plus something like that.
Oh gosh.
They have
Really nasty. Yeah,
that will
yeah,
be a
okay.
substring, right? Word will be a substring in that case, not a subsequence, right?
Yeah, string itself, substring itself. So given a large string and a set of words, you need to find whether those words exist in the tree, or I mean the bigger string or not.
Hmm.
Okay. Mm. Yeah, then try
Will
should.
that approach work here when we are looking for subsequences?
No, I don't think so, because you need to pass over multiple things, right? Uh, I mean, you need to use,
Sequences.
in subsequence, you need to skip characters.
Right,
Yeah.
right.
Hmm.
No.
Interesting. So you form a try and then you start iterating through your S. So every time you hit any of those character, you go to that node of a try and then start going ahead like a DFS fashion. Yeah, maybe.
Yeah, again go to the initial and then start.
Yeah,
Yeah.
and then only it might be O of n. Yeah,
And some M is for what? The length of words.
length of S.
Words. Oh yeah, shared some. But that isn't a string matching problem. We using KMP also you can do, right? You have to find that
KMP,
particular pattern in the string.
yeah, KMP will be again like n into m.
No, yeah, but with rolling as it will be in O of n.
Yeah, but you have multiple words, right? So you need to compute KMP for every array, right?
Hmm.
Yeah, no, that's why that n into m is modified. I mean, optimized by using KMP, which brings it a linear time algorithm.
That is n plus m, right?
Yeah, n plus m.
Yeah, but here, I mean, you have the m is m here is multiple words.
Oh, a set of words. Okay.
Yeah.
Yeah.
But
Yeah.
that's
Then
good to think on that lines. Yeah. Yeah. Thanks for bringing this.
Ronnie is asking something like, can you confirm time complexity for binary search approach?
Yeah, that is what we discussed now, right? Yeah.
Mhm.
So we don't have a very clear answer, Ronnie, but it's like you can say whatever that words length, words array length multiplied by each and every string's length and log of s, right? So
Yeah.
if that whole thing is Rm, then it will be m log s or m log n, something like that. Yeah. If n is equal to the size of s.
M log n. Yeah, what
Yeah.
I'm saying.
Yeah. Because s size is big, and that is what we want to not be spend more time on that expensive length, right? Yeah.
Length, yes.
Okay. Well,
Yeah.
let's go to this.
Now, next one is like increasing order search tree. BST is given, and we have to rearrange the tree in order so that there should not be leftmost node in the tree, and every node has no left child and only one right child. Okay, leftmost node will become the root, and every node will not have any left child and will have only right child. So this like
Yeah.
your one left node becomes root, and then 2 and so on. 3, then 5.
So they are saying like you take a binary tree, well formed or whatever formed binary tree, good binary tree, and then just convert it into a linked list, right? Almost
Yeah,
like that.
somewhat, yeah, because
Hmm.
they are chopping off the left side. Only one way, yeah, kind of that.
Hmm. So yeah, whenever binary tree problem comes, even if it's easier, it's
Recursion makes it big.
yeah, it's like you have to really think well. If you can actually solve this problem iteratively, it is more easier, right?
Yeah, but mostly trees
Was there.
recursive only. Code becomes much more
Yeah,
smaller, right?
because whenever I see it's an in-order tree, the in-order tree algorithm, iterative algorithm is easier, right? It's not that complex like the other ones. Other ones also not that difficult, but the iterative is slightly easier. At least you don't make mistakes there, right? Because if you go in this recursive version, you can find some things, and you'll have to be very careful with
Yeah,
all the base cases and everything. Yeah.
you'll have to use stack in that case, iterative one.
Yes, you'll have to use that.
Yeah.
But here, what could be brute force?
Brute force, like you do the in order traversal of this tree. Since it is a BST, it will give you a sorted tree, right? If you do in order traversal.
Yeah, you get what you say like an array, all the values in that array,
Yeah,
and then you form another tree.
tree of
Tree of
topic.
topic.
Yeah.
So basically, put all things in a list or array,
Hmm.
and then traverse your list and create a new tree out of it.
Right.
Yes.
So
So
that could be a brute
Linked
force.
list.
can't we avoid that intermediate array directly modifying the
Yeah,
tree itself?
yeah. So that's like how we can think about intuition. Now we have a array here, so how we can avoid that?
Yeah.
So basically, what it will become is, I think one. If there one there, what is that down?
Yeah, middle one.
Yeah, one is there. 1, 2, 3, 4, 5.
So it would become 1, 2, 3, 4, 5, 6, 7, 8. So now we can construct another thing, like take this and make it this right, this right, this right, this. So that is doable. Now, can we do while doing this? That is a question. While doing a in-order traversal.
Yeah, that will
Hmm.
be linked.
Yeah, we can do that. I think we can pass on a variable, uh, like anything, maybe say prev, and the first time we hit the leftmost part, we initialize it to the leftmost tree, and then every time we do this, prev of next equals to our current root node, and make our root node as the prev.
So
What we call
basically,
the
we have a hack. First time when we see something, we'll
yeah
make one as head, and after that, whatever is my previous
that would be this.
dot right would become something like current. So if I've seen one previously, its right should become this.
Right.
And
And now you make
previous
the cur as the previous.
left should become null.
Yeah, that's important. Yeah.
Yeah,
And then keep on doing like that.
recursively. Yes.
Yeah, and make the prev as like cur as the previous also. Prev equal to cur.
Yeah, so that will be at the end. Yeah. Right.
Yeah.
Okay.
And then on top of that, keep on doing that in order, what is it? Current dot left. And then in order current dot
Right.
right.
Okay. So yeah, recursively in this case, you don't have to do much, just these two
Simultaneously.
calls and then yeah.
And then additional check for capturing the head.
Oh yeah, that has to be done before this one. Yeah. So it will be an if-else condition here, right?
Something, yeah, like that.
The head is null, then initialize it.
Right. So this is the complete algorithm, right? Implementation.
Yeah, basically earlier we are doing the same thing. Here we were putting in a list.
That you are doing here.
This and this would be same, and then we were putting that current in the list. Now we are just trying to see if we can play with the current with some variables and do some magic here.
Yeah.
We haven't yet made use of this fact that this is a BST.
Yes.
We are
Yeah,
taking
even if we had a normal tree also, it would work, right? Yeah, makes sense.
No, they want increasing. That will come in a that will be a BST, because when we do BST in order, then only we get like an increasing.
Yeah, otherwise you'll have to take the array and sort it in other traverse.
Oh, where is it said that we need it increasing?
I think this is increasing order.
Okay, but in the
Yeah, heading
question they
is
do not mention it that way. Like, they want is just in order traversal.
Yeah, because their input is like that, so automatically it
Yeah,
happens,
BST,
right? Yeah.
So yeah, I think they should have mentioned here, but this I think means the same thing.
yeah, otherwise why don't?
So there are two interview questions like this. So conversion of a BST to doubly linked list and doubly linked list to BST in place actually.
Right.
I didn't get what they were saying.
So he's telling like making this as a doubly
There
linked.
are
Oh, okay.
But is it mean like one pointing to two and two pointing to one? Is it like that?
yeah, one should point to two and two left should point to one.
No,
Oh.
but it is a tree. How can you point to two? Backward pointer should not be the right.
No, it's possible. So you have a current. Its right will become two, and whatever is two, two's left will become current, something like that.
Yeah. Yep. And then you convert that to a PST. Okay.
I think there are what is mentioned. There are two questions: converting BST to this and double linked list to BST.
So you're saying there are two?
These are interview questions I was trying to say.
Yeah. So how do we do with the other way of that, like DLL to BST?
So you take the middle node and convert that left half into left subtree and right half into right subtree.
And recursively again take the middle of left half and right half, right?
Yeah.
So for that, the DLL has to be sorted, right?
Yeah,
Yet
so
it
both are actually sorted itself. BST to sorted, DLL sorted doubly linked list, and sorted doubly linked list to be balanced by reverse tree.
Yeah, if you
Right.
don't have it, then it's not possible. Yeah, that's true.
Yeah.
So, but in the doubly linked list, you are using all the nodes of a tree node, right?
Yeah. So
Okay.
you use that left as previous and right as next, something like that.
Hmm.
Right. So I think this would be n log n, right? DLL to BST. The way you explained, like finding the mid and then calling for both of these.
There are some optimizing as well here as well. So instead of taking the middle node, they
Yeah.
actually try to get the size and they pass the size and do it. It can be done in
Right.
OAuth.
Yeah. So that O of n is when you start from the bottom, like from the starting of DLL only.
Yeah, yeah.
Yeah.
Yep, good. Yep, thank you. So, you want to run through any implementation or this is fine?
I didn't code it, so I don't have to code.
Okay.
I
Okay,
oh,
you
please
have
share
it.
it. Yeah, I have, but I don't have that approach. Like what you say. I mean, pointer shifting. I just did a normal what you say in order traversal.
Let
Like
me
first loop, value, and the right, and keep on appending inside the what do you say list. So that list will already be sorted, right? And now once the list is sorted, so I pop the first element of that and put it into my tree node. Tree node is a class which will have val left and right. And as long as your list is not empty, so take that node, make the root, and to the left you do none. So that left will not be there, and to the right you just assign this tree. And in that tree again with this variable. At last just return the root tree.
Okay, okay. And this gets accepted, right?
Yeah, it gets accepted.
Okay, okay, no problem.
But that is a bit more, what do you say?
But your time complexity is also good, not that bad, yeah.
It's like 32 year, 32 ms.
I
Yeah.
think time complexity would be the same. Only the space complexity would be better. Like,
Okay.
the way.
Passes will also be less. Like there directly is doing everything on the go itself, on the fly itself.
Yeah, in place.
Yeah, if you do the iterative version of in order, then it will be almost the same, right? The way we are doing over here.
Yeah,
Mm,
you'll have to use a stack and
right.
code will become a bit more.
Yeah.
Like here we are using only 3 lines for in order.
Yeah.
But in interview, I think they intentionally asked to implement in iterative way because here recursive implementation of this traversal is easy. I mean, it's got by hearted only, left, root, and right.
No, but recursive coming those conditions, even though are very small, it's critical. You need to
Exactly.
understand properly that. Yeah.
One mistake. Yeah.
Yeah. So does anyone has to share those?
Yeah, if anyone has other one, share it.
Okay. If you know, ask you to share it.
Ashim is there,
Mhm.
So I think that's what we have discussed.
Right, right. So you pass head to root, and in that, rev.right is actually pointing to the root.
So because by this time we don't have previous.
Hmm. Yeah. And you are doing prev equals root outside of the if else because it's common for both.
Yeah.
And by that time we already done with left, so we can make it null.
Yeah, both of them. That's right. Yeah, that's a very
Order
concise
of,
way of implementing. Yeah.
so it is order of n only. Mine is n log. No, mine is also order of n.
Yours is also order of n.
Order of
But
n,
Yeah.
yeah.
there is a extra memory
Hmm.
Extra
of list.
array I'm using.
Yeah, here there is no extra memory.
Yeah, that's good.
How do you check if the previous is not no? The first time previous is no, right?
Mm-hmm.
No, we are going to
He is not checking previous at all.
You check it? Yeah, but then
Because when he checks for head equals null, okay, then he sets head to root, and at that time also he sets previous to root. So previous won't be null after that, right?
no.
Right. Yeah.
And this is a in order traversal. So that means you will always come like this. So first you will hit. After that only you will start come to this block. So technically this will always happen first, and then only the else will start executing.
Oh yeah, correct. So if you do the iterative way, you put everything in the stack. At the end, you come when you are to the leftmost of the tree, then you actually pop from the stack, right? And then you go for the right one. Yeah.
So here it will go like this, and yeah, and then it will start then it will do something. So basically, it will visit this after visiting this guy. So that time we'll have previous.
Yeah.
Okay, I have to leave now.
Okay,
So,
no problem. Thank you. Yeah.
see you guys. Bye-bye.
Yeah. Thank you. Bye. I will share the iterative version quickly because we already
Yeah.
here. And then we can. Okay. So this one was. Okay. So in this iterative version, okay, this was the recursive. Is this the iterative version? Yeah. So, well, I'm actually putting this in the root helper function. And then this is what the iterative, it's a big code, right? So I'm actually using this answer outside. And then I run through this, I put a stack, then I have two, one is the current and one is the end root. Okay, so this is my while loop because
What is
I've
the end root?
assigned. Well, end root is actually when I'm doing it here, you know, when I'm actually assigning my answer. Okay, I gave a very bad name there, but that's fine.
Yeah.
So it's like what we were thinking about that head, right? So this will be the head for that, yeah, sort of. Okay, so I go in here, then I do this y current, they put that in the stack. Okay, then when I come here out of the stack, I just pop it out. Okay, so when I pop it out, so here actually why I'm using end root is like, you know, differentiate between whether it is a null starting one. Okay, so then I assign this one because end root actually I'm assigning to current. Yeah, I could have done a better way. Instead of that, I could have just using answer also if it was null. So need not use that though. Yeah. So the pre-when answer something like that because my answer will be the head of that tree, and this was like pre, right? What he was showing. So then in this case, when I come here, the same thing, right? The same conditions apply here also.
You have to the right current
Yeah,
and that
and then this last is the one what we do for the general iterative
next.
version. Yeah.
Yeah.
Yep.
Yeah, it also looks good.
Yeah.
Unless
But it's like as you said, you also use a stack. In your
stack.
case, you use a list, right? So and you go through each and every one. Yeah.
But I'm using implicit stack in recursion also, right?
But that you already have to go, right?
Yeah, yeah.
That for everyone. Oh yeah. In this case, you just move. Okay.
Yes.
Yeah, it's as good as what Asim showed.
But the iterative version, yeah. Yeah, sometimes it's good to actually revise the iterative versions of these
Yeah, they
in order.
sometimes ask
Yeah,
also.
they ask very. Okay.
But yeah, uh, uh, rather than recursive, iterative is better every time, right?
I actually think it is easier to implement sometimes, right? Because recursive, you might miss some of the critical conditions, and at least you can verify them when you are doing iterative. That is what I feel more comfortable, therefore. But I think if you are able to do with the iterative, there is nothing like it. Sorry, the recursive, there is nothing like it. That's the best. The way he came, very clean solution, correct? What Asim came up with that.
Yeah.
That was a very clean solution. Yeah. Okay.
Yeah.
Then we can stop the recording and then.
Yeah, sure.
Okay. Okay.
Recording. Yeah. Yeah, we can then wrap it up.
Yeah. So this Sunday, do we have that session on grabbing car for KNP?
We'll have to check the sign up page. I think we had. I'm not sure.
Okay.
So that page is on the site, right?
Yeah, I haven't seen that.
No, I saw that link one day. Rogers shared it after that. Maybe I think it will be. Yeah.
So next Sunday we are having on the Rabin car.
This coming Sunday.
Okay, this Sunday.
I'm not sure. Like I think.
Come again? What do you say?
I'm saying I'm not sure, but I think it will be.
Okay, no problem.
Yeah.
Yeah. Okay.
Okay then.
Okay, thank you guys. Yeah.
Thank you guys. Yeah.
Thank you, Sam. Thank you,
Thanks.
Ronnie.